So finally, the inverse function theorem. Except we're probably not going to get to prove the whole thing today. We're going to make an important first step, and maybe next time we'll prove the whole thing or perhaps another important step. So what we'll do today is reduce the inverse function theorem to a simpler case. So let's get the statement up. So assume you have a C1 function from an open subset E of Rn to Rn, and notice these n's have to be the same. And assume you've got some point A in E such that f prime at A is an invertible linear map, is a bijection. So the linear approximation is at A is invertible, then the inverse function theorem says that the function f is invertible in some neighborhood of A. So then there is some neighborhood U of A. So by neighborhood I just mean an open set that contains A, and it's going to be an open subset of E. I don't know if I really need to say that. That might be implied by what I'm going to write. Such that, and I'm going to follow the order that I wrote these in originally, but for some reason I wrote the most important fact second. If you take f and restrict it, then this is injective. If you take f and restrict it to this neighborhood of A, then it's injective. And also, the image of U is going to be open. And finally, if you restrict f to U, so if you restrict f to U, then that's by 2 and 1, that's a bijection from the open set U to the open set f of U. So here we usually give this one a name. Let's call it V. So this is our definition of V. So if I take this, the inverse of f restricted to U, which is a bijection from U to V, if I take the inverse, then that's a bijection from V back to U. And the third point is this is a C1 map. All right, so this is the inverse function theorem. And what we're going to do today is reduce it down to a simpler case. So we're going to reduce down to the situation where f prime A is not only invertible, but it's the identity linear map. So we're going to show that if we can prove the inverse function theorem, if we can prove a version of the inverse function theorem where this is actually not assumed to be invertible, but it's assumed to be the identity map, then we will have proven the inverse function theorem. Okay, so let's assume all the hypotheses. Or, let me not write proof since I'm not going to finish it today. So let me write claim. It is sufficient to prove the inverse function theorem in the case f prime A equals the identity map. So that's my claim. So this is the claim that I'm going to prove today. And then next time we'll look at proving the inverse function theorem in the case f prime A is the identity map. So we'll start by saying assume the hypotheses of the inverse function theorem. meaning assume that F is a C1 map and F prime of A is an invertible linear map. Then here's what I imagine. So let's say this is E, and here's A somewhere in E. And here's Rm, and A gets mapped somewhere, F of A. So F is doing this. And we're not imagining that F is necessarily invertible. That's not the point. But we're imagining that the linear approximation to F near A, which is F prime of A, at least near to A, that linear approximation, the linear approximation F prime of A, so linear approximation to F at A, we're assuming that that's invertible. Now, since it is a linear approximation, it does sort of, if you look near enough to A, it does approximate the mapping F to F from points near A to points near F of A. So F prime of A does help you to approximate what happens to these points. So one thing you can do to try to think about how to flip things around and send points back to try to invert F, actually, is you can try to go back along the linear approximation of F. So map points here by F to here, and then map them back using F prime A inverse. So what I'm saying is, consider this composition. Go from E to Rm, like this. Sorry, it should be Rn, not Rm. Go from E to Rn like this, and then go from Rn back to Rn, probably in E or very close to E at least, via F prime A inverse. Remember, F prime A will be a linear map from Rn to Rn, so its inverse will be a linear map from Rn to Rn. So basically go forward along F and then back along F prime A inverse. So this is an attempt to sort of undo F, but it doesn't work perfectly, right? Because F prime of A is not like F. It's only a linear approximation. But hopefully you're somewhat convinced that it's worth at least thinking about this composition. Of course, F prime A, so it's not like F prime A actually is approximately equal to F. When we say it's a linear approximation, we're saying it tells us differences of outputs of F from F of A in terms of differences of the inputs away from A. But what I'm about to do is take a derivative. So an affine shift like that, like replacing this by it plus a constant function, that's not going to affect the derivative. So none of that really matters. So let's just look at this composition. Well, f is, both of these functions are differentiable that I'm composing. F is differentiable because I assumed it's a C1 function, right? And this is differentiable because it's a linear map. F prime of A is a linear map, and the inverse of a linear map is a linear map. So these are both differentiable. So I can take the derivative, and the derivative is given by the chain rule. So let me look at the derivative at A. That's going to be take this linear map, take its derivative, and evaluate at f of A, and then compose that with f prime of A. Okay, but hang on. If you take a linear map and take its derivative, at every point, the derivative of a linear map is itself. Right? So the derivative here, no matter what I plug in, be it f of a or something else, I'm just going to get the linear map itself. The derivative of a linear map is itself. And look, now I have a composition f prime of a, this linear map, composed with its inverse. What happens when you compose a linear map with its inverse? You get the identity. When you compose any function with its inverse. So this is the identity function on the set Rn. Alright, interesting. So when you look at this composition, it's differentiable everywhere, and it's differentiable at a in particular, and the derivative at a is the identity linear map. So the idea of the claim here, that it's sufficient to prove the inverse function theorem in the case where the derivative is the identity linear map, is the idea is if you could prove the inverse function theorem instead of for f, for this composite, then you would have proven it for f. Let's see if I can convince you of that. Then you should believe the claim, if you become convinced of that. So let's call this composite H. So let H be this composition, and it maps E to Rn. So to prove the claim, which is that it's sufficient to prove the inverse function theorem for the case where the derivative is the identity, in order to prove the full inverse function theorem. To prove that claim, we will prove that if the inverse function theorem applies to H, then it applies to F. So let's prove that. So assume the inverse function theorem applies to H. Then, what does the inverse function theorem say? It says we can get a neighborhood U of A. Notice A is where, this is H here, A is where H prime ends up being an invertible linear map and ends up being the identity linear map. So we can get a neighborhood U of A such that those three things happen way up in the statement of the inverse function theorem, except for H. So 1, 2, 3. The important one here, 2, is H restricted to U is injective. 1 was the image of U, which maybe we can call that V, is open, an open set. And the third one is when you restrict H to U and take the inverse, then as a map from V to U, this is C1. Okay, so the goal is now to prove, using this fact, the goal now is to prove the same thing, but for F rather than H. Then we will have proven this claim, which says that it's sufficient to prove the inverse function theorem with the identity here in place of F prime A. Okay, I hope that's clear what the general strategy is. So now I just need to verify that all these hold for F. So let's check out 1 first, then let's check out 1 first. So I want to prove that f of u is open, right? Well, f of u is very closely related to h of u. It's so when I apply h to the open set u, I'm applying this composite. So f of u must be, let me just do this. Take this linear map, f prime a, and apply it to the inverse of f prime a of f of u. Okay, so I took this set and I applied an invertible function, and then I applied the inverse of that invertible function. So I get back to the same set, right? And then on the inside here, what you see is h of u. So this is f of h of u. Sorry. This is f prime a of h of u. Now, is this open? Well, I know h of u is open. Is the image of an open set under a linear map open? Not always, but yes if the linear map is invertible. Let me just state that here and then go verify it on the side in a moment. So, since f prime a is an invertible linear map, and h of u is open, f prime a of h of u is open. Therefore, f of u is open. And let's give that a name. Now that this is the last time we mention it here. Let's not call it v, since that's what we've called h of u. Let's call it v naught, I guess. And I promised I would verify this. If you take an invertible linear map and apply it to an open set, then you get an open set. So let me just verify that off to the side here. So assume L is an invertible linear map. Say Rn to Rn. And let's say O subset Rn is open. Then L of O is the preimage of O under L inverse. So think of it this way. It's the preimage of O under L inverse. This is open because the preimage of an open set under a continuous function is open. So this is open because L inverse is continuous. And by the way, L inverse is continuous because it's a linear map. Linear maps are continuous, and the inverse of a linear map is always a linear map. Okay, so that's the justification for that. All right, great. So if one can prove that this maps some u to an open set, then f maps u to an open set. So the number 1 for h gave us number 1 for f. Now 2. So h restricted to u is injective. What about f restricted to u? So to try and relate f restricted to u to h restricted to u, let me compose with f prime a and f prime a inverse. And the domain restriction can happen at the level of f, or it can happen at a later level also. right? Remember, these are just linear maps, f prime a and f prime a inverse. They're maps from Rn to Rn. So there's no danger in composing them with f restricted or unrestricted. So what I'm trying to say is the domain restriction is perfectly okay if it takes place after this first composition. Nothing changes. So then this is f prime a composed with h restricted to u. Okay, h restricted to u is injective, and f prime a is a bijection, right? We assumed it's an invertible linear map, so this is a bijection. So therefore, this is a composition of an injection with another injection, so we get an injection. So the idea is both of these are injective. And finally, h restricted to u inverse is C1. Can we use that to prove that f restricted to u inverse is C1? So let's look at f restricted to u inverse. So to relate that to the inverse of h restricted to u, I'm going to need to compose with f prime a, but I actually need to make the compositions happen on the right side rather than the left side, since the inverting is going to flip things around. So just bear with me and see what happens here. So I think if I do it this way, so right now I haven't changed anything, right? I've composed with an invertible function and then composed with the inverse of it. Then I think here, if you look at this, this will be h restricted to u inverse. So hang on, what was h again? H was this composition, f composed with f prime a inverse, right? So maybe I'll just, before I try to do this all in one go, let me move it down and first think about what is h restricted to u inverse. It is f prime of a inverse composed with f, that's h, right, restricted to u inverse. Now the restriction can happen inside, like this. And when you invert a composition where both of the functions you're composing are invertible, that works like this. And we've already verified that f restricted to u is invertible. That was up here, number 2. And here I got inverse twice. So yeah, so this is what happens when you invert a composition of functions, right? Yes, so what is in square brackets down here is h restricted to u inverse. So this is h restricted to u inverse composed with this thing. And look at that. F restricted to u inverse is a composition of two C1 functions. This is a C1 function because it is linear. Linear maps are C1, right? They're differentiable, and their derivative is themselves. So the derivative is themselves everywhere, so the derivative is actually a constant function. And that's a continuous function. So linear maps are C1. So this is C1, and this is C1 by our assumption 3 up here. So due to the first video of today's lecture, the composition of C1 maps is C1, this is C1. is C1 by, let's see, it was lecture 6, part 1. All right, so I think that proves the claim. Okay, so what we've done so far is basically carried out a first step for the proof of the inverse function theorem. This is our full inverse function theorem, and from the assumptions of the inverse function theorem, we reached this situation where this composition is a C1 map, and its derivative at A is the identity. And we decided that if we can prove the inverse function theorem for this composition, meaning if we manage to prove 1, 2, 3 here for H, where H is this composition here, then by all the argumentation we made here, we will have proven the inverse function theorem for F. So next time when we revisit the inverse function theorem and go to finish the proof, we will be able to approach this, but with an extra assumption, which is not just f prime of A is invertible, but something much stronger, f prime of A is the identity. This is not the exact approach Rudin is taking in his proof, but my hope is that taking this step, which includes what I think is a kind of intuitive component here, trying to use the inverse of the linear approximation of f to go back and undo what f has done. I'm hoping that taking this step is going to vastly simplify Rudin's approach, and then we're going to follow the same approach Rudin follows, but with that extra simplification that we will get to assume f prime of A is the identity.